Good afternoon, BC Calculists. You should have this page here in front of you, the series test review page. We're going to talk about series today. You probably saw that on your quizzes. That's our goal for this lesson. But I wanted to start with what I thought was some really cool data. So first of all, I got this chart. This chart is not from the paper listed above here, but it's a list, and it's kind of just a breakdown of which FRQs from each year's test fit into which category on Unit 10. So Unit 10, series, sequences, Taylor series, Maclaurin series, that kind of thing, it will definitely be on there. It'll be tested pretty heavily. Specifically, question 6 is almost always a series question, especially in the last 15, 20 years. This test has been going for a long, long time. The AP Calc test has. And all of this is just the data through 2007. So this doesn't even have anything kind of since the most recent adjustment to the AP test. But it does include, I think, some pretty good breakdown of what you expect to see. So on the FRQ specifically, manipulation will be on there very, very likely. And that's something that we practiced about 2 weeks ago, right? So go back and look that over if that is very, very vague to you. Also, derivatives, antiderivatives, that's the same as manipulation, but it all kind of fits into that same bucket, right? Our goal for today is to talk about writing Taylor-Maclaurin polynomials. So this category here, and then Taylor-Maclaurin series category here, and then do the ratio test, because I think our ratio test is a little too weak. We just aren't quite precise enough with our notation. So those are the two foci for today. But I did want to share with you, this is an awesome, awesome paper. I had no clue about some of this sweet history of the AP Calc exam. Here's what it looks like. It says the evolution of the AP Calculus AB test from 1955 to 2018. Man, I read it right before I was trying to go to sleep. I couldn't sleep afterwards because it was so interesting. Turns out the first several years of the AP exam, from 55 to 1969, it wasn't split into AB or BC. So they just had calculus. We can see that down here. It was just calculus. Only 11,000 kids were taking it. And then in 1969, they decided we gotta update this test here and make it more applicable to what kids are seeing in colleges. So they split it into AB and BC. The AB test initially had a lot more pre-calc stuff on it. And since then, look at how these numbers have just ballooned. We're up to 447,000 kids who took the test in 2018, compared to the 11,000 in 1968. So that's crazy. Calculus has a lot of people taking this test. I just thought this history was kind of interesting. There used to be pre-calc questions on here. Now there's definitely zero. Another interesting fact was that they used to use the same test for a few years in a row. So I don't know if I have this chart easily accessible, but they had one version in 1969, and then they didn't make a new test until 1973. And then they didn't make a new test until 1985. The internet was way less popular. It was far harder to get answers and to pass on what you know. And so they just didn't change it. So I thought that was interesting. Read through that paper if you want. It doesn't really add much for calculus knowledge, but I thought it was kind of cool. But we're only going to do 2 questions. One at the bottom of this page, one on the back side, and then you'll have time to work on your AP project section for the day and potentially get started on your week 5 homework. Your second to last homework assignment of your high school calculus careers. How crazy is that? So I chose this question because it has both pieces of what we're actually working on for today. It has writing a third degree Taylor polynomial. So write a polynomial, and then it has use the ratio test to find the interval of convergence, or really just the radius of convergence. So we're going to do both of those here. To start, it says this Taylor series is about x equals 5 for a certain function. It converges to all values of x. Cool. This is only giving me my derivative. So this chunk right here is just the derivative. And then it gives me one single point. And we need that to try and write our function. So if I want a third degree Taylor polynomial, I'm going to write this as p sub 3 of x. So this is my polynomial of degree 3. And we always start with f of 5, and then we add the derivative evaluated at 5 divided by 1 factorial, but I don't really need to write it, times x minus 5 to the first. You would not need to write this on the AC test. I'm writing it out to show where each piece comes from. But plus the second derivative evaluated at 5 over 2 factorial times x minus 5 squared. And then the third derivative at 5 over 3 factorial times x minus 5 to the third. This is our Taylor series. This is really poor handwriting, but it is our Taylor series. The thing that most students have forgotten this year has been this factorial in the bottom. Especially when we're given a derivative function like this, we just kind of assume that that's everything, right? But that's not the entire coefficient. We have to definitely use the factorial in the bottom also. So let's evaluate here what we need, and we'll write this thing piece by piece. So p sub 3 of x equals f of 5. Well, that's given us 1/2. F prime of 5, what's my first derivative? So we're really plugging 1 in for n to find the first derivative evaluated at 5. If I plug 1 in for n, negative 1 to the first is negative. N factorial is just 1 over 2 to the first, that's 2 times n plus 2, so that's 3, okay. And then I could say over 1 factorial, I could put this down here in the bottom. 1 factorial, there it is. Doesn't change anything, so I'm just going to erase it. But that's definitely my coefficient here. And then my factor is still there, x minus 5 to the first. It's x minus 5 because I'm centered around 5. I don't know if I mentioned that, so that's where that comes from. And then we have 2 more, so these 2 will go a little bit quicker. This will be, it'll be plus, right, because it's the second. N is 2 in this case, so negative 1 squared is 1. 2 factorial on top. Well, there's going to be, let's see, 2 squared, so that's 4, times 2 plus 2, that's 4, times 2 factorial, times x minus 5 squared. We don't need to simplify this at all. You can, but we're going to use the derivative part for our radius of convergence down below. So we really don't need to, but you could if you wanted. And then the last one, minus. Now n is 3, so it's negative 3 factorial over 2 to the third times 3 plus 2, that's 5, times 3 factorial times x minus 5 to the third. I'm pretty confident in this Taylor series. The most common error is forgetting that factorial in the bottom, or simplifying incorrectly. I saw that a couple times on your test. So just be super careful. This is something that if we get this part wrong, it's tough to justify points on other parts of the question. So we just got to be super precise here. Use that Taylor series formula. Keep practicing that on Delta Math if it's a hard one for you, because there's some pretty good sections that walk you through it very clearly. Part B, find the radius of convergence about x equals 5. So we're going to use our general term, and I like to write this as a sub n. So we're writing a sub n. This is like my general term, and we're going to do the ratio test to find this radius of convergence. Why ratio test? It's almost always ratio test because I've got factorials, I've got exponents, I've got all sorts of goofy stuff. So here's my a sub n function. I know the derivative part is negative 1 to the n times n factorial all over 2 to the n times n plus 2. There's the derivative portion. But then I also have to include this n factorial on the bottom as part of my Taylor polynomial formula. And then around x equals 5, so it's x minus 5 to the nth power. Here is my general term. This is my a term. I'm going to simplify just a little bit because then I won't have to when I do the ratio test. So n factorials cancel. We'll leave negative 1 to the n here for now, but obviously once I do the ratio test, that's gone. And then on the bottom, 2 to the n times n plus 2. Okay, cool. Here's my general term. When we're doing ratio test, use this one. But the most common issues I've noticed, forgetting to do limit notation every time, being a little bit too quick to cancel out everything, And then number 3 is just, I think we just get confused about what cancels, like how many degrees can cancel all over the place, right? So this is a tricky question. Let's write out our ratio test super precisely. So we're going to write the limit as n approaches infinity of, remember it's a sub n plus 1 divided by a sub n. So my a sub n plus 1 term is plugging in n plus 1 everywhere I see an n. I'm not going to write that negative 1 term. That's just the alternator, right? So we don't care about that. All right, and then if I divided by a sub n in the denominator, I'd actually multiply by the reciprocal. So I'm just going to write the flipped version of that in the numerator here. So 2 to the n times n plus 2 all over x minus 5 to the n. Just be super precise here. We need to show whatever x values makes this thing less than 1, that's where it converges. So let's start by canceling some things. Let's rewrite this here. Limit as n approaches infinity. Make sure you write that every time. Some of us have been a little bit too sloppy here. 2 to the n plus 1, that's 2 to the n times 2 to the first. So my 2 to the n's will cancel, as will my x minus 5 to the n. So I'm just left with x minus 5 times n plus 2 all over 2 times n plus 3, whatever this handwriting is going on here. Okay, and I want this thing to be less than 1. This is where we're using some horizontal asymptote rules. So like n on top, n on the bottom. Really, for this to be less than 1, the coefficient x minus 5 over 2 has to be less than 1. So really what we're saying is this has to be less than 1 for the whole thing to converge by the ratio test. That's our goal. From this point, we can split it up. We can say negative 1 less than this less than 1, but really we just need the radius. So my radius is actually 2. I multiplied by 2 there. If you wanted to find the interval, remember negative 2 less than x minus 5 less than 2, and then add 5 to each side, so 3 less than x less than 7. If you were trying to find the interval, we would have to test our endpoints. If you want the radius, stop right here. So we're going to just be clear here. Our radius of convergence equals 2. Some FRQs will say find the radius and the interval. Those are doozies of FRQs. We got the radius here. You'd get to the interval on this bottom step, plug 3 and 7 all the way back into the original series, see whether it converges or diverges. Those are probably coming up on your practice AP test. So this is our topic for today. Use this as a reference. Your section for today is, oh, don't look at that, that's a key, is just another set of 2 parts of an AP question. So take 15 or so minutes, try and knock this thing out. The key is on the next page. Use that as you need to, or use your classmates as you need to. The homework for this week is posted. Here it is, homework week 5, due Friday, May 3rd. Senior signing day is on Thursday, May 2nd, so we won't have class that day. Just make sure you get this done before Friday. Good luck. Here's your section. Pull out your computers, do that in your packet. Ready to go.